So, in order to think about normal distributions, we really need to tackle continuous random variables first. So when we say x is a continuous random variable, we mean x being a random variable that takes on values from a continuous range of values. So we have this association from the sample space S to the set of measurable outcomes, which are represented as numbers. So in the real number set, and X is this association that allows us to take these events and put them in terms of numbers. So it'll usually be the entire real number line. So something like everything from negative infinity to infinity, not including infinity and negative infinity. So you can go as fine as you want. So 0 is a specific outcome, and maybe perhaps also 1.1111111 repeating forever, as well as anything like 1/2 or negative 3.2. The important thing here is we have arbitrary fineness in our precision. So any one individual outcome represented as a number is different from something that's right next to it. It could also just be, an interval on the line. So it could just be, we're looking at the line segment 0 to 10. And anywhere in between that, like 3.5 or 2 pi, all of those values are possible outcomes for this random variable. That said, that means that when we are measuring something much more precisely, we are typically using continuous random variables. So for instance, if we think about x being student attentiveness during a lecture, measured in terms of time until distraction in 10 minutes. So imagine you walk into your 8 a.m. In-person class. You sit down, the class begins at 8, and you're attentive until 8:05, right? So if it's measured in minutes, then it could take on some value like 5 minutes or 4.2 minutes. If you're particularly attentive, you'll be, paying attention a long time. And it's subject to, how precise our measurement is. But in theory, this is a continuous random variable, since we can measure parts of a minute with arbitrary fineness. For that reason, these variables tend to come up quite a bit in the sciences, whether that's physical or social. And to actually work with these, let's actually think about what the probability functions might look like. So, unrelated to that example, let's assume we have a continuous random variable x, and it has the probability function such that for all x between 0 and 5, not including 0, but including 5, that probability, and we want to be clear that it's not a direct probability. This is different. It is unclear directly from this how to get the probabilities themselves. So the name is a little misleading. We also call this the probability density function. This is an example of something called a piecewise function because we have different rules depending on what our outcome is. So what this random variable does is it takes our entire real number line. Imagine we're, for instance, throwing darts, right? So on this interval from 0 to 5, then we have this increased likelihood of hitting our dart there. But our dart can hit anywhere between 0 and 5 to as fine a point as possible. So it might look like we're saying if it's 0.2, then that value is not changing. And everywhere else, it's 0. So for any x less than 0, and for any x greater than 5, not including 5. So this is what the probability density function looks like. And how this actually measures probability is we're only interested in the area under that curve, under the density function itself. So our regular notion of summation for finding a probability here breaks down. And that's because we can't say, the probability of x being between 0 and 5 is as simple as saying probability of 0 plus probability of 1 plus probability of 2, ... That's not what's happening here. In fact, we would be adding or taking the summation of for all x between 0 and 5. So this is, and it may take little convincing to show you this, but this is actually impossible because there's infinitely many numbers between 0 and 5. So, in other words, to find the probability, we have a new approach. So to find the probability of, for instance, x taking on some value less than a being 4 or 1 or 2, then that's going to be the area under the curve from leftmost to the line x equals a. So in other words, we're going to take some invisible vertical line and just measure the area underneath. Oh no, that's not what I wanted. Why would you do that? There we go. And that area is equal to the probability. So for instance, the probability that x takes on a value less than or equal to 3 is going to be the area between 0 and 3 bounded below by, or bounded above by the density curve. So this line, this magenta line, that gives us the area that we're going to bound, which is, in this case, it looks like a rectangular area, right? So, so in order to find area, remember that we need, of a rectangle, we need the height and the length, or the base length, I should say. The base length in this case is from 0 to 3. That's going to be 3. And the height we already said was 0.2. Because that's how we defined the density curve, right? And that means our probability is 0.6. So the likelihood of finding, in other words, if this is our dart, right, and it can hit between 0 and 5, and if it lands somewhere lower than 3, then our dart has a 60% chance of that happening. And so what's more helpful is if we define what we call the cumulative density function, or CDF. All probability that we're interested in this context for continuous random variables will be in relation to the cumulative density function. And we define that as capital F of x, x being that value in the support, that measurable outcome. And it's the probability that our random variable is less than or equal to x. And formally then, or not formally, but practically then, if we define the probability density function, what we're saying is this is the area under the probability density function curve from the leftmost support value, which is sometimes negative infinity, so all the way from way out in the negative infinity, and to that value x. So that defines the upper value. And so because we need this to be a valid, these need to give us valid probabilities, then we should have the two following concepts, which is that 1, for all x in the support, so for each outcome, we have a real number given by f of x, the cumulative density function. So it's going to be some real number between 0 and 1. 2, f is an increasing function of the support. So the larger, so as x gets closer to 1, sorry, not closer to 1, but gets larger in value, f of x gets closer to 1. And importantly, we need that f is increasing. So such a function would look like something like this. So as you go from 0 to, I don't know, infinity, it might look like, here's the value 1. Maybe it'll look like this. Or it gets closer and closer to 1. Maybe it reaches it, maybe it doesn't. But at any given value, right? So for instance, maybe this is 1, and maybe this is 2. Then you know that the probability of being less than or equal to 1 has to be less than the probability of being less than or equal to 2. And there's more formal ways of writing all of this, but that's beyond the scope of our course.